Hey everybody, nice to see you all here in this morning. Well, today we're going to talk about costs with PostgreSQL and data modeling. Hey Marco, welcome. This title actually is a bit misleading because we're not going to model data here, but we try to understand how the data model can influence on the cost and performance when we are working with database, right? So go, move. Here you go. Okay. So a little bit about myself. My name is Charly Batista. I'm the Postgres tech leader at Percona. I've been working with Percona for more than 6 years now. I'm used to be based in China, so I lived in China for a long time. I had to move to Brazil before the pandemic started, but now we're planning to go back to China because my wife is Chinese. And I do really love to work with database, especially with performance. So performance is one of the things that I like the best, not only with database, but also with development and languages. So I really like to learn in new data structures and algorithms. So those are the things I really like to study and practice. I've been working with database for more than 20 years now, so we may find some team together. I'm always open to learn new stuff, right? So we always learn new things. And one thing that I always tell people is pay attention to the basics, to the foundations. Sometimes we are working with database for that long time, 10, 15, 20 years, and then we forget about the foundations. And the foundations are very important. And that's why we have so many bad softwares today. Because the developers, they don't like to learn and to reveal the foundations because, well, they're boring. People like fancy stuff, AI and all those fancy different names that we have today, right? So you can find me here on LinkedIn and also a few more contact information by the end of this presentation. Okay, so what we're going to talk today, what is the objective of this talk? So we're going to have an overview. We're going to review some concepts on the storage, and it's funny how it's important, how it's simple, and how many people misunderstand those concepts. And they are super important to understand many times how we lose performance with simple stuff, including this one that we're going to see today. We're going to see how Postgres stores data and how it's different from a few other databases, for example, MySQL, and we understand why Postgres chooses a lot of times to do a full table scan. Sometimes we just create that fancy, nice index that we believe is going to solve all our problems, and then the database just goes to a full table scan. That's disappointing sometimes. We see how Postgres organize the free map, because one question that we have many times is vacuum goes to clean up space on the database, right? But how does vacuum knows which space it needs to clean? Does it need to run all the pages inside of the table, inside of the database? What if we have terabytes of data there? That's going to be quite expensive, right? And then we will come to the summary, and obviously, hey, thank you guys to be here. And here we go, back again. So as I mentioned, this talk is not really about modeling. And we're not going to learn here how to create tables, how to create relationships. That's not what this talk about. We're trying to understand how the model influences on the cost that we can have and on the performance. And you'll see that they might be quite tied together one to another, especially when we start understanding how the space is organized, how the disk is organized. And we're going to start with SSD, DRAM, and CPU. So this is a nice picture from Google that shows the hierarchy on how memory is organized inside of a computer, right? Usually when we learn, like, study computer science, this is one of the first things we should learn how that works. And as you can see here, I still put magnetic types, right? Because they still exist. People still use them, especially for backups. So memory, as we call here, the price decreases. We go to the base, the pyramid here. So magnet types, disks, and SSDs, they are a lot cheaper than the cache memory and the register CPU. But for the other hand, the performance increases as we go to the top. So as we get closer to the CPU here, the performance is going to be faster, but the price is also going to be higher. And that's why we have so few memory, for example, for the CPU cache. When you buy a nice CPU, like for a desktop, and you go see, okay, I want an Intel i9 or whatever. So usually what we check how much cache memory that CPU has, right? Because we want performance. But how does this improve performance? How is this memory so much better than the other memories? And why is this so expensive? So memory by default, it's volatile. Main memory and CPU memory, they are volatile. It means if we lose electricity here, everything gonna be raised. So they are volatile because the components they are built on, they need to always keep electricity in there. And usually the way they work is with high and low signal. We tend to see that the computer is binary, right? So 1 means it has, 0 means it doesn't have. Actually, it's not that way. So when we go to electronics, the components, we have a level of voltage that we say that above of that level of voltage is 1, we have electricity, and below of that level of voltage is 0. It's common to be 3.5 or 5 volts, depending on the component. So if you have a component that works with 5 volts level, everything that is close to 5 volts, like 5, 5.5, 4.7, we say that we have 1 bit there. If everything that's below that threshold, so it's 0. It means that if you have no voltage at all, that's 0. So it lost all the information. Memory is not able to keep the information. Different from the hard drivers, right? So, and why one memory is more expensive than the others? So the trick is the component, what they're built on. So the closer to the CPU, the smaller the components are, so more information we can put on the same space, on the same inch, more information you can put. And because they are smaller and they're closer together, they're a lot faster. And obviously, the material that they've been built is different. That's why the cache memory is a lot more expensive, because the ratio per inch of the transistor we have there is a lot higher than the main memory. So they are more dense components, and they are more expensive. And that's why usually we have the cache memory in megabytes. And now the main memory is gigabytes, soon enough going to be in terabytes, right? So, and what about the disk here, the I/O? Well, obviously the components are different. For example, the spinning disk, they're pretty simple. They're just magnetic types. That's why they are super slow. SSDs, they're getting better. They're getting closer to the main memory. But they're still slower than the main memory. And we also have another problem. We say that the CPU is not able to work with data on the hard drive. It doesn't matter if it's SSD or it's a spinning disk. And the major problem is, as you see here, the CPU doesn't have physical access to hard drive. Every time that we need to work with something, let's say we do a select, The database needs to fetch that data from disk. It will ask for the memory controller. The memory controller will get that data from disk, put inside of memory, and then the CPU starts working. And still, the CPU uses the memory as slow storage. The CPU doesn't work directly with data in memory. Even though we tend to believe that CPU is going to get and start working with the data in memory, it doesn't, because memory is still super slow compared to the CPU. We have a huge, huge difference in performance. So the CPU will load those information from the main memory back to the cache memory inside of the CPU, and that's when the CPU starts working. And still, as the name says, it's cache. Everything that's here going to be put inside of the register, and the CPU is going to start work with that data. CPU works with data in the register, and the register they're super, super small. So what it does, it pulls the memory from the cache memory to the register, works with that information, and then put back to the cache. So if we write an application that works with too much or data that can't fit in the cache, the CPU is going to start to access main memory too frequently, and then we start to have a slowdown in application. And it can be even worse. If it doesn't fit in the memory, it goes to hard drive. Remember, CPU doesn't access the hard drive. It doesn't matter if it's magnetic or if it's SSD, because it doesn't have direct connection. And then we start to slowing things a lot. And that's why we have so many optimizations to keep cache hot. Always keep information in the cache, because it's going to be things a lot faster. Okay, we have basically 3 different types of accessing when we go to I/O. And here I/O, we're going to talk about I/O doesn't matter, can be disk I/O, memory I/O, network I/O. So for the CPU, they are always the I/O. CPU actually has 2 types of operations. Either I/O, it either reads and writes information, or calculations. It's move bytes from one position to another to do math. That's the only thing that CPU can do. CPU cannot do anything else other than those 2 operations. So then I/O is very important. And we basically have 3 methods of access. We have the random access, we have the sequential and directly access. So the sequential access is for I/O the better one that we can have. The directly access is very specific. It only happens in the register and the cache, so we're not going to basically talk about them. What matters for us are the sequential and the random access. As the name implies, the sequential access, it gets one byte or one information after another. The random, it doesn't keep the information close to each other. So it goes, for example, to the information here on the address 1, and then to the 5, and then come to the 3, to the 2, to the 8. So you can imagine that on a spinning disk, that's very expensive, because it needs to spin, and the head needs to move. Sometimes we believe that the speed of the spinning disk, what's the most important for the performance. Actually, it's not. It's the head. What makes the spinning disk so slow is the mechanical mechanisms, like, sounds weird, but yeah, the mechanism for the head. It needs to move, and that's a lot slower to do not compromise the disk itself. Can you imagine the disk running like 7,000 times per minute, and that physical head moving in a way that's not scratch the disk? That's what makes the spinning disk so slow. And on the random access, it needs to keep moving. So if you have a sequential access, you just put the head there and let it spin. It will be a lot faster than the random access. On SSDs, we don't have that problem. We don't have moving parts. Everything are electrical components, but they still is lower. Obviously not on order of magnitudes, like on a spinning disk, but it still is lower. Depending on the SSD, they're going to be 3 times, the sequential 3 times faster, 5 times faster. So depends how the manufacturer builds the driver. Here is just a comparison from how fast or slow they can be from one to another, the SSD, the random to sequential access. So we have here on a hard drive a spinning one. So we can see that reading this same information here, we had around 6.1 milliseconds on random access. Actually, 6.1 seconds, sorry. 6.1 seconds on random access, and on sequential, 53 milliseconds. So those are order of magnitude. That's the difference on a spinning disk from random to sequential. And that's why when you go for your database, for example, use a database that you need to do a B3, whatever index that you use is expensive, because index or B3 per nature, they do random access. Remember how a tree is organized? It's not one information after another. We need to go skipping pages here and there to traverse the tree. Tree is expensive to traverse on random access disk. So we have here for SSDs, as we see, it's not that much. This one, the test that I did on my laptop here, it was around 2 times faster. So we have, from different vendors, we can have different performance. And obviously, depending on the test, my test is a really simple one, it's just writing in blocks. And talking about blocks, the files, everything on when we save something in the disk, everything is stored in blocks. When we ask an information from the CPU, one CPU needs something. CPU is going to the disk and read a file, a text file. So we have a huge text file, and we want to read only the first line. First line has, like, this is the first line, right? So pretty simple. We probably have here, I don't know, 100 bytes. I don't know how many characters we have here, but let's say 100 bytes. So because the way the information is retrieved from disk, it's always retrieved in blocks. The disk stores and retrieves information in blocks of bytes. And by default, most of the OS and most of the manufacturers, they work with 4 kilobytes block. So every time that I ask to read only this here, it will get 4 kilobytes block from disk and put in memory. So if I have an operation that I need to work with all of this data, it's cheaper to get all of this data in one batch, because you're going to read the whole block anyways, and then you can process that information. This is one thing that we need to keep in mind, that the CPU only retrieves data in blocks. So because of that, all the databases, they also work with blocks. So when we do a select, and we have a very simple one, all right? So can you guys see here? Right? So I'm going to create I suppose I have this table here. Let me do select stuff from T heap where ID equals 1. Well, if I don't have, well, yeah, the table doesn't, well, ID doesn't exist. Okay, yeah, the first problem. No, I don't want autocomplete. No rows. So second problem, but that's easy to fix. Now I have 1,000. So I did this very simple select. Let me just put this a bit up here. So see this very simple select. It didn't bring much. It's probably like 20 bytes here. Well, 20 bytes, not 20 kilobytes. 20 bytes here. To put those 20 bytes here, the database had to read the whole block. And we'll see that on Postgres, the block is not of 4 kilobytes, it's of 8 kilobytes. So then how does Postgres organize the data internally? So the Postgres organize in a data structure it's called heap file. And the funny thing is that this data structure is super simple. They do nothing. They just put one block after another. As we see here, so we have a huge file. If you have like a file with 1,000 blocks, going to be block 1, 2, 3, 4, 5, and that's it. There's no order, there's no special information, nothing. You just put one block after another. And because we put one block after another, we can imagine that it's quite cheap to traverse that data structure, right? Because it's just one after another. You just ask, if you're in a spinning disk, you just ask them to read. It's just a spin, you put the block, that's it. That's simple. It's sequential access by nature. Heap file is sequential access by nature. And that's the faster, easiest way for the database to retrieve and recover data. So as I said, the heap files, they split in blocks. On Postgres, the block size by default is 8 kilobytes. And there's a reason to be 8 kilobytes. Remember that I said most of the OS, they have 4 kilobytes block size. So it's 2 blocks of the OS. And this alignment is very important because every time that we align with the size of the block, of everything that's the OS or the CPU works, we only need one operation to retrieve them. So if we ask one block or one page, so we're going to use blocks and page here with the same meaning because usually the OS call blocks and the database they call page, but they're basically the same thing, right? So if we ask one block or one page from the database, that's 8 kilobytes, it's just one read from the disk, one I/O. That's it. In one go, it gets those 2 blocks from the database. It's fixed. We cannot change the block size. Yep. So your question is, would that be more efficient if the default block size on Postgres would be 4K? So not really. Yeah, not really. No, would not be more efficient. Actually, for reads, would be more efficient if it was larger. Because if it was larger, you force your file to be more sequential. Remember, your database is not the only guy running on the operational system. So when you do an I/O, you write something on the disk, and then someone else writes something else on the disk. So the disk is spinning. Let's consider the spinning disk. The disk is spinning, but it will try not to move the head. If you have empty space just after your block file, you're going to write another disk, something else from the other application. So now, instead of have sequential pages here, you're going to have a hole here in between one and another. And this can be to another sector for the spinning disk. So if you had larger block size, for this circumstance of writing, is more efficient than having smaller, because instead of creating like sparse files, now we have a huge sequential one. Okay, your question is, just because the page size is much larger than the information that we saved here, we're going to waste a lot of I/O, right? So this has to do with one thing that I was supposed to have told you guys, but I probably didn't. Let me see if I have here. Oh, I don't have here. That we call locality. When we talk about cache, we have 2 different types of cache. We have spatial cache that is in space, in time, and locality cache. It means that the chance that when you get one data, the chance that you get something closer to that data is a lot higher, the probability is a lot higher than get something that is further from that data. So if you read this page here, the chance that you need data that's close to this page, like the next page, is a lot higher than we need data from the other page. So this is an optimization. So when you when you retrieve only a few bytes from a select, like I did a select one, the chance that I get data from the very same page in another select is higher than I get from another one. So Actually, that's going to improve your performance because the database will already have that information in memory. And when you do the next select to get the next data, it doesn't need to go to this disk anymore. That's why a lot of, not only database application and OS, they do what we call prefetch. So when we ask one block for the OS, they always read a few more, they prefetch and put in memory because the probability of you need that data is higher. So if you don't need that data, that's fine, because it's just run everything in one batch. Remember, for I/O perspective, it doesn't do much different that if they are sequential, you read 1 or 5. That's basically the same. We only got one I/O. But for performance, if you already have that in memory, that's a lot faster. And okay, what if I don't need? Well, I wasted memory. No, really, because that is space in memory is cheaper to just be evicted. That's one of optimization when we talk about cache. But that's a pretty good question. So back here, yeah, there are a page of 8 kilobytes on Postgres. There is no configuration we can change. So the page size is changed during compilation time. If you want to change, you need to recompile your database. And I do not recommend doing that unless you really need and you really know what you're doing, because that can cause a lot of problem. So for one perspective, reading more data can make things faster. But if you do prefetch too much, just like you asked, then now you can make things slower, and your database can be incompatible with the full versions, right? So it's a problem. And the only way to change the block size later, let's say I change it here for 16 kilobytes, and I want to come back to 8 kilobytes. The only way is doing a logical dump. We need to do a logical dump from here and then read it in another database. Well, if I have like 100 gigabytes data, that's not that bad. But like if I have few terabytes of data, that can take a week. So it's not recommended to change them. Okay, now that we know it's organized in block, what we have inside of those blocks? This is basically what we have inside of the blocks on Postgres, right? So the blocks on the beginning of each block, this is the 8 kilobytes block. In the beginning of the 8 kilobytes block, we have a header. This header here will keep some information from the block itself, right? So the header is the first 24 bytes. All of them they have. And we have this what we call item identifiers or line pointers. And then we have the data itself, what we call tuple. So it's interesting to understand that the database does not store the data here in the beginning, sequentially. The data starts to be stored by the end of the file and grows towards the middle. And there is one of the reasons is one optimization that they call a hot. So databases, they usually do not change data in place because it's expensive. Let's say we do an update. It's not that the database will go there and change that data in place. Postgres, what it does is, let's say I change this tuple here, right? The last one, it will get this data here, put in memory, change that data in memory, and then save the new data as a new tuple. And we'll mark this one as removed, as deleted. So because this one is marked as removed, as deleted, every time that we do a select, you just ignore this one, because it's removed. So we're going to get the data from the new data from this new tuple here, right? And we have basically two problems. First problem is obviously we're going to start have a lot of trash inside of the pages, right? So that trash is what the people in Postgres they call bloat. So when the table is bloated, it's because we have a lot of those trash here inside of the table. And if we are not careful, our table can get bloated really easy, because every time that we do an update, it will create trash inside of here of the page. Also, the same happens for deletes. Every time that I do a delete, this guy will be here. So the file size doesn't change when we do a delete on the Postgres. We'll see soon. Oops, that's not what I intended. So to solve this problem, Postgres has a tool that everybody loves. They call vacuum. So if you talk with a Postgres database, everybody gonna love that too, right? So really, from deep of their heart, if they could blow that up, they would do it right now. So it's a hated, it's a needed evil, right? So the vacuum will come here, and those tuples that are marked as removed, they will just clean up and allow the space to be reused. There are different, not types, but levels of vacuum that you can run. The default one, that's a good misunderstanding. The default one, you clean up here, but will not reorganize the table. The table size you still keep the same, but now we have space inside of the pages, and every time that we insert something, this space can be reused. If we don't do the vacuum, this space cannot be reused. That's the difference. If you do a vacuum full, it will reorganize the table, it will rebuild the table, and we'll clean up and reclaim the space that we have. And then we will see that is being cleaned. All right. Now that we see the table, time to see the layout of the row. This is how our row is organized inside of the database. So every time that we insert one row, one of those tuples here, it will have a header. All of this is the header of 24 bytes. With a lot of information from the data. This is the data. Here we have the data. On the header, we have information about the null, if that we have nulls inside of the table. We have the address of that row inside, the physical address inside. We're going to see soon how that happens. And one thing that we also have is this little guy here. We call padding. Anybody knows what padding is? Empty space. But why? Why do we need empty space here? Is it a no? Alignment. Yeah, alignment is the word. But alignment with what? CPU word size. CPU has what they call word size, actually basically the architecture size of the CPU. When we work with a CPU that's 64 bits, that's the full Intel architecture nowadays, it means that the word size of that CPU is 64 bits, 8 bytes. But why do we need to have alignment with the CPU word size?
Because the minimum access unit is a CPU core.
Yeah, the minimum, but what does that mean? Why do you still, what is the difference? What does it cause? Why is that so important? We want our CPU to work in the best optimized way, right? So let's say here I have 9 bytes, and up to here, no, actually, let's do better. Here I have 7 bytes and 1 byte here on this padding thing, right? And I only want to retrieve this information. So because the CPU is of 8 bytes, it just needs 1 cycle, right? But what happens if I have, this one is 4 bytes, the end of the data is 4 bytes, and then next 4 bytes. Now the CPU, even though I'm going to still get 8 bytes, but because there is no alignment with the CPU word, the CPU will get 8 bytes, half of the information, and the next 8 bytes, the other half of the information. So I needed 2 CPU cycles to get the 8 bytes that I need. That's why alignment is so important. Because if the data is aligned with the CPU word size, for that amount of byte, like information, 8 bytes, I only need 1 CPU cycle. If it's not aligned, I will need more than 1 CPU cycle. Well, that doesn't seem to be too bad, right? But what if we have millions of cycles that is needed to process the information? Remember, when talking about database, the order of magnitude of the amount of information is huge. So in order to not waste CPU cycles, what the database is, not only Postgres, but most of the database, what they do is they align the data with the CPU word size, and they put just empty spaces here. That puts only empty spaces. And this is basically what we're going to talk today. So, and what I'm going to do, show you guys here, is the end of the talk, because we may not have enough time to get to the end. So I'm going to create this table here. See? Let me drop just to make sure it doesn't exist. Well, fine. It's a pretty simple table. I don't have fancy data types. I don't have archive. Only integers and 1 boolean. Boolean is 1 byte. So integers depend on the integer. This int of 2 is 2 bytes. Int of 8 obviously is 8 bytes. The default int of nothing is 4 bytes. So I won't end the numeric value here. If I'm not mistaken, there's around 6. I don't recall on top of my mind. But the numeric is not aligned, right? So it's 1, 2, 3, 4, 5, 6 columns. Simple table, nothing fancy. I'm gonna insert with random values, right? 1 million rows. And then I'm gonna do a checkpoint to force them to be saved to the disk. And I'm gonna check the table size. So the table size is 73 megabytes, right? Nothing huge. But what I'm gonna do, I'm gonna create another table with the very same columns. Just a second. So I'm gonna, doesn't exist. I'm gonna create using a select because I don't want only to have the same columns. I want to have the same data. This is the very same table that I have the 1, 2, 3, 4, 5, 6 rows. The rows are all the same with the same names because it's the same data type. It's a select from the original one. The only thing that I changed is the order of the columns inside of the table, right? I'm gonna run here. 1 million rows, as we saw. I'm gonna do a checkpoint. And I'm gonna check both of the tables. What do you guys guess? They should have the same size, right? They're the same table. Yeah, 73, 72, negligible, right? Not much difference. They have the same data types, the same columns, the same data. Why one has 73 and other one 57? Why do we have 22% different size here? This is padding. This is this guy here. And this is all we need to know for today. Obviously, I have a few more things, but this is all we need to know today. The padding is really bad for the database, for performance and for cost. Can you imagine you save 22% on your bill for the space? And remember, everything that's on disk eventually going to go to memory. If you do a select, that padding is also going to memory. Really good question, Marco. So your question is if I put all the integers in the beginning, right? Not only they, remember, they are all integers. Yeah, that's I'm going there. Remember, they are mostly all integers, but I have one integer that's 2 bytes. 8 bytes, all exactly. So the thing is not only 8, but 8 aligned. So if I had for, oh goodness, here we go again. If we had here, for example, this is an integer of 2, right? So if my table had an integer of 4, that is the default integer, so instead of waste 6 bytes here, because I'm wasting 6 bytes, because the next column here is integer of 8. Remember, it will try to align, right, with 8 bytes. Here they can join they both together. We'll only waste 2 bytes in this case. So the alignment counts not only with the data type that we have, but also with the next data type. It's the combination of the both. Because in this case, the next data type is an integer of 8. This is already has 8 bytes. So then I need to fill the previous one with the needed empty spaces for them both to be aligned. If I had here another integer of 2, well, that would be perfect. 2 plus 4 plus 2, 8 bytes. So no padding needed whatsoever here. And in this case, remember the Boolean I said is 1 byte. We're wasting 6 bytes here from this Boolean to the integer. And I ask you guys, see that we have a lot of new values here. Does the new influence on the size? The null value. Okay, so what do you guys think? Does the new influence? Yeah, the new influences, but probably not the way you guys are thinking to. So how Postgres stores new? See this bitmap here? Postgres creates a map of all the columns that we have in the database. In this example here, I have, let's come to the beginning. We have 6 rows here, right? Sorry, 6 columns. We have 6 columns here. So it will create a map with 6 bits. Each bit represents the position of the row inside. So this one can be null. So it's the first one on my table. So the first bit gonna be 0 or 1. If it's 1, means it's null. If 0, means there is data. The difference that nulls change the information here is because this data will either be insert the space of be there or not. That's the only way. The null doesn't store the data, the null, the 1 byte there. It stores 1 bit for Postgres. Yeah, in the map, and that's it. Yeah.
So there's a, if you go to slide, right, there's a,
Yep.
each row has a row header and you have a null bitmap, right?
Yes. Yes. Because you can, the null it changes from row to row. So you may have one row that has null on that value and another row that it's filled. But I didn't understand your question. Yes. Has 1 million rows, yes. Yes, each row has a row header. Okay. Okay. Okay, I think I understand. So if you already have a table with data and you have some nullable columns, when you do an outer table to insert more columns with more nullable columns, yeah, it has to change. And one of the reasons why outer table does a lock, because the data structure of the table has to change and the file has to be updated. Yeah. And that's one of the reasons why some outer tables are more expensive than others on Postgres, right? Even we have the same amount of data, some can take more or less time because the data type as well and how the new is being stored.
So my experience is if I add a column with not null, it's like pretty big. But with the null, or it's probably the other way. With the null, it's pretty big. But if I do not null, I think it takes like.
Yeah, your question, your experience is when you add a column that is nullable, it's a lot faster than when you add a column that is not null. That's true because the column that, remember, it's just a bitmap here. When you add a column, it's going to add to the end. And because it's nullable, won't be much of difference here, and that's a lot faster. That's one of the reasons. The second reason is when you add a column that is not null, you need to have a default value. So it needs to update all the rows, not only to update the bitmap, but also to add the default value. So that's why it's usually, if you can afford to do an outer table and add a column that's nullable, do it because it's going to be a lot faster. And after that, you can update in batches, so it doesn't put too much pressure on your database. Update the first 1 million, the next 1 million in batches, so you get the same result by the end, but it will be not faster, but not so much pressure on your database. And the lock, that is very important, would be really fast, really quick, right? All right. So we're talking about the padding. So it depends on the data type, right, as we saw. And this is just an example that I showed you guys. So what happens if you create all those kind of stuff? So it can be very expensive, really, really expensive. And bonus thing, toast. Do you know what is toast? It's not that nice thing you put there, and some people like butter, other people olive oil, peanuts, butter, whatever. Apart from that one, do you guys know what's toast in Postgres? Toast is a workaround. Let's put it on this way. They call the oversized attribute storage technique. Remember that I said the data file is split in pages, 8 kilobytes page. What happens if you need to store some data that has 10 kilobytes? Does it split in 2 pages? Postgres doesn't split the data. If the data that you're trying to store now to save doesn't fit inside of the 8 kilobytes, it will save it somewhere else. It creates another file, and this file is what they call toast.
But you said that any file in Postgres is based on 8K.
Yes.
In any case, it will be split on that file into blocks.
So your question is, all the files on Postgres are 8K blocks. So even the toast is going to be split in 8K blocks, right? Yeah, that's a good question, and that's correct. So the difference is on toast, we have basically a linked list of blocks. So the first block, when we, let me go back here. So when we save the data here, instead of we have the data, we're going to have a pointer, a physical pointer address to the beginning of that data on the toast file. So in the beginning of the data, you're going to have a header, and they always point to the next block and to the next block and up to the last one. Like, so it's an easy way to explain, but it's basically we have a linked list. So in the database, we read all that one and put in memory.
So it was sequential?
Always sequential. Well, yeah, logical sequential, right? And as it saves in one batch, yeah, it's always sequential. It will always be sequential. So this is what we call toast. And understanding what is toast and how the database stores the data also brings another problem. Remember my select here. It was a select, well, the first select that I did, it was a select star, right? Somewhere here. Okay, just found it. So I did a select star. In this case, nothing fancy, they were pretty small. But let's take in consideration that I have a table user And my table user, I have the login, password, name, address, and I have what they call profile. And in this profile, I have a JSON file. Well, it's not uncommon, right? Nowadays you have, or I have a text or something like that. So the problem is, this profile here will go to a toast file. So if I need to do a login, and I do a select star, that toast data will always be read into memory. Always read that data in memory. If it's a large data, so we're going to get a lot it's going to be a lot slower if I do a proper select, login, and a password. If I need a name, login, password, and name. So if I never mention the profile in my select, Postgres will never open that toast file. That data will never be retrieved because it's not needed. So if we do a select star, like many of the developers and ORM they do, we always get that information from. It's another way of optimization. Doing nothing, you're already optimizing your selects from the database. Yes. So that's the toast. So as I mentioned, the default threshold to go for a toast is of 2 kilobytes. So if your data is larger than kilobytes, that's gonna go for toast, right? And the other one is the free space map. Remember that I mentioned that it would be super expensive if Postgres has to read everything to get the free space. So Postgres has what they call a free space map. So on the free space map, every position here actually is a unit of 32 bytes. Why they do that? Because they want to store the page here on this tree using only 2056 bits only. So it's a lot smaller tree, and it works traversing the tree from the bottom up. Let's say I need to find someone that has a slot that is at least of 4 available slots, right? So 4 is 32 each slot, so I'm saving something that's around 132 bytes. So how does it work? It will go here, down. These are the page numbers, the page numbers here down, and we're gonna see here which one has at least that amount of empty space. Well, the page 0 doesn't have. The page 1, the page 2 only has 1. The page 4 only has 2. This page 8, 3. So the page 2 I found has 4. It goes up to the 3. So the 3 here, it only has, this one only has 3. Doesn't fill. Go up. Well, we found one that has 7. And then it traversed the 3 down. We found this guy here that has 6. So we found them. We don't need to go to the data file. We can only traverse this tree here and find empty slots. This is also one way that vacuum works, and the indexes, they can also use this one to check, in some cases, if the page is valid or not. So the free space map, every time that we create a table and we start to delete or we create empty space, where we have multiple pages, we'll have the free space map here. It has the same name of the page, the OID, with the extension FSM, and it's usually really, really small, a few kilobytes. And it's a very efficient way to do. And this is also updated by the vacuum. So see how some stuff are very important on Postgres. The vacuum, for example, it cleans up the space on the page. Because remember, when we delete, that page is marked as removed. It's not removed. So that space is still there. It won't come to the free space map. if you delete all the tables or the whole page, even though we have all that information being deleted there, is be occupying the space here until you run the vacuum, and the vacuum does the cleanup and update the free space map. Until that, we cannot use that one. And what happens if we insert a new data, even though we have the whole block empty? Postgres will just create a new block, because it's not free. It's marked as deleted, but it's not free. It will be free when the vacuum goes there and does the cleanup, and that's when we can start inserting again. So the summary is Postgres stores data in a data structure that we call heap files. They are sequential, really fast. That's the fast way to read. So that's why a lot of times Postgres ignore indexes, because indexes, they are stored in trees, and trees are expensive to traverse. They are not sequential, they are random access. So to be able to use the index, it needs to be a lot better than do a full table scan. So if you create an index that the cardinality is pretty low, for example, when you select, you're gonna select where, whatever, gonna retrieve 30% of the table, very likely the database is gonna do a full table scan. Because it's cheaper, gonna be faster. And the database can parallelize the full table scan. It can do it parallel. So for the database, that's gonna be a lot cheaper. Cheaper not always is faster, keep in memory. So it's cheaper, it's easier, but sometimes it's still slower than doing the index. There are ways to force, not using indexes hints, but we can reorganize the select to make it faster and use whatever we want the database to use. So the file is divided in 8 kilobytes block. There is no order, zero order inside of the data file. So it's going to be in the order that we insert the data in the beginning, but when you start updating, you just start shuffling the data here and there. The data can change from a block to another. So there is zero, no order guaranteed on the heap file. Keep that in mind. Postgres controls the free space for each block on a map file, like the free space, and also it uses that to expose the visibility of the block. How many data empty there, if some visibility in there. Deleting raw records and updating will not change in place, so delete will not remove, will mark as removed. Update is not change in place, we'll do a delete and an insert. So it's two operations, right? It uses the natural alignment of 8 bytes internally, and we saw how problematic that can be if we do not proper organize the tables. And every time has its own alignment and can cause different patterns. So we are on the top of the hour. If we have questions, we can answer later in the booth. Thanks a lot, and that's for today. Thank you.